Alright, I'm going to try to get through this problem quickly because this one involves a lot of scrolling, because there's a lot of calculations, and the longer my videos get, the more the visuals start to lag, and that's not good if I'm scrolling a lot. Okay, so we have a matrix A, and we want to do QR factorization, both reduced and full. So we just, let's see here, I decided to go with classical Gram-Schmidt, and you just sort of go through it. You just follow the algorithm. You take the first column, you find its norm, you divide by its norm, then you take the second column, you do this thingy to get R12, then you take V2, and update it by subtracting this times this, and then you set R22 to be the norm of this, and then you divide to get this. And so, therefore, the reduced QR factorization is just A equals Q times R, and Q1 is here, Q2 is here, and then this is R11, this is R12, this is R22. So yeah. So now to obtain a full factorization, what we need to do is we need to take Q1 and Q2 and extend it to an orthonormal basis of R3. We need to add another column to this Q, and it needs to make this a unitary matrix. But thankfully, we see that, so we got this one dealing with, this is just E2, and then here we've got, this is like 1, 0, 1, but normalized. So if we took 1, 0, minus 1 and normalized it, then that should be orthogonal with everything. You can sort of just visually see that if you take the inner product of this thing with itself, then for the same reason that this has norm 1, this will have norm 1. Then if you take the inner product of this vector with either of these two, you can see that you'll end up with 0. So then setting Q3 to be this vector gives us Q1, Q2, and Q3, which is indeed an orthonormal basis of R3. And so therefore, our final QR factorization of A, we just take R and we just add zeros to the end, and then we take that Q3 and we put it here. And so this is a full QR factorization, and so we're done. And finally, what we have to do is we have to look at B. And the first column of B is the same as the first column of A. So the first few steps in this QR factorization are going to be identical. We're going to get the same Q1, we're going to get the same R11, we're going to get the same V1. And it's given by this. And then if we continue from there, let's see, I caught some typos here from when I had copy and pasted the formatting. But anyway, we take the second column of B, which is this. Then we take Q1 star it, and we get this. Then we do some more math, and then we just keep going, and we eventually get this. And this is Q2. So the reduced factorization is given by this, Q times R. Here it's a little more complicated, but similar idea. So if we want to do a full QR factorization, we need to take Q1 and Q2 and extend it to an orthonormal basis of R3. And unfortunately, in this case, it's not as easy. There's maybe if you're like really good at this stuff, then you can just eyeball this and be like, oh yeah, I know what to do. But I don't see any obvious way to do that. So we do Gram-Schmidt orthogonalization, like the one that you would do in basic linear algebra classes in order to find orthonormal bases. We actually do that here. So it ends up being very similar because it's, of course, it's a very similar method. So how does this work again? So we take, first of all, we start with just we need to add something else to Q1 and Q2 to get a set which spans, or which is a basis for R3. And so if you just look at this, well, if you were to add E1 here, then you can sort of convince yourself that if you were to put this matrix here, just put this E1 here, then you could row reduce it to the identity. Because let's see here, the E1, how would this work? So obviously you can combine this with this, and that will give you like a 0 and a 1 here and a 0, and then you could get rid of everything else from there. No, if you add this to this, you get 1, 0, 0. No, you get 1, 0, 1. And then, yeah, you would just go from there. You'd row reduce the identity. And so, anyways, this is a basis for R3. So then, we can find Q3 using just standard Gram-Schmidt orthogonalization. So we find U using this procedure. We let U be E1 minus the projection of E1 onto Q1, then minus the projection of E1 onto Q2. And so we get a whole bunch of inner products. And a lot of these computations end up being simple because E1 is easy to work with, but we end up with this vector. And so then once we have this, we need to normalize it. So this is going to be orthogonal to the other two vectors. This will be orthogonal to Q1 and Q2, but we need to normalize it. And so to do that, we let Q3 be this vector here divided by its norm, and you just do some math and you get this. And then by construction, this set is orthonormal, and therefore our full QR factorization is given by this. You just take what you had before and you add this thing into this column, and then you just add some zeros there. And if you just like sort of eyeball this, the inner product of Q1 and Q2, or the inner product of Q1 and Q3 is 0 for the same reason that the inner product of Q1 and Q2 is 0. The two things the minus sign will cancel them out. And then if you take Q2 and Q3, these vectors here are weighted in such a way that everything will sort of work out nicely. But yeah, so that's how you do this exercise. And so this exercise is pretty much just getting you to actually by hand do some QR factorization. And so there you go. That's all there is to this exercise.